Right, I have some variable, I have a few observations, I have tons of missing observations, and I just plug in the average, or the mode, the most common answer on the survey for all of the ones I didn't observe. Great, I can do inference now, but of course, I'm going to massively underestimate the variance in that question. So let's look at some typical approaches that people will think of to do and do in practice, and at least make a comment about them. So this one that I've been talking about is like mean or mode imputation. So if it's a continuous variable, we might plug in the mean. That doesn't make much sense for a categorical variable. For an ordinal variable, maybe we'll plug in the middle one, or the something that's like a mean, add numbers and then take the mean, or maybe the mode for a categorical. Of course, here, this pulls down, at a minimum, pulls down the standard deviation and understates the variation. Right? So if there was any signal, or if there was any dependence among that variable and the other ones, we've weakened its link to the rest of the things, right? We've sort of lost the ability to see its dependence. I mean, we'll still pick up something, but it'll be much weaker. Dependence is harder to see. Okay, so a common thing in longitudinal studies. So in time series or longitudinal studies, a very common thing is to do last value carry forward. You have a series of things. You don't know someone dropped out at some point here, and so you just fill in rest of twos, right? Sometimes people think about this as being conservative. If it's an increasing sequence, if it looks like an increasing sequence, for example, it seems like it's conservative to stop the increase by just pegging it somewhere. Maybe we're doing some kind of a study where we have a treatment that's being applied, here, and then we have this dropout, and we hope the treatment keeps making it get better, but we don't know, and so we just say we'll keep it that way. Of course, it can also go in the other direction. So because if the underlying process had a mean reversion property, it was like something as farther away it gets from the origin, it sort of has more pullback, right? Like even if it's just random draws, and an extreme value for that random draw causes censoring, right? So like someone has a really, really bad day, they drop out of the survey, or they, it's a treatment for a drug, and one day someone gets really, really sick, and then they just like don't want to deal with it anymore, right? But it could be that the next day they felt better, right? So it could also be that this type of last value carry forward could exaggerate effects if it's picking up the extremes of a mean reverting process. So you have to understand what's going on better to decide whether that makes sense. So we can do various kinds of deterministic imputation. And by which I mean not even building a model. This is often a very good one to do if you have a logic. Right, so you have a survey that kind of asks the same question different ways. Some of the questions don't get answered, and you can kind of figure out what what the answer had to be in order to be consistent with the rest. So use the logic, consistency, or sometimes just physics to constraints that are on your set to constrain and pick a value that is consistent with the other values. a method that is kind of nice because it stays within the model. And I sort of like this one because it stays kind of, all the other ones we've talked about are kind of meta models that step outside of what we've been talking about in the class. This one stays in the one, which is that I have a categorical variable. Yeah, say the outcomes of the categorical variable are like red, green, blue. Right? And sometimes they don't answer. So we just say it's either red, green, blue, or it's missing. We just decide that being missing is one of the values. Everything has a null possible value. And we just throw that in the machinery. Right? So there's no change in machinery needed. We just add a value. This is nice for us because unlike a situation with continuous variables where you have to decide how to think about an unreported real number, if everything is categorical, it's no big deal to just add another category. We know how to deal in every situation. Right? We know how to do polytomous logistic regression, and we know in every situation how to just add another category. So we can do that, and then nothing special needs to be done, as long as we can conceptually think of it as a valid outcome. Something that does work for continuous variables and also for categorical is to add a new variable. So this is adding a new value of a single variable. This is like x could be one of those things. We can add an indicator variable. So just throw another variable into our log linear model for missingness. So we have like m. Make that actually just one of the things that we're predicting, or one of the ways in our table, or maybe multiple of these if we want more than one variable to be allowed to be missing. Maybe there's x, y, z, mx, my, mz. Okay, great. So we had a 2 by 3 by 3 table, and now we have a 2 by 3 by 3 by 2 by 2 by 2 table. And we can continue with our categorical analysis of it. You can also, people use this often with continuous variables. So you might have some variable r, which is a real number, and then we have r is missing. And when r is missing is turned on, we just plug in 0 for that, or some sort of neutral value for the missing thing. Of course, that can cause some bias, because all of a sudden we have a bunch of zeros. The mean of this is not going to make sense anymore. Things like that. So even if you plug in the mean, the dependence will cause problems. Causes bias. So any way you can think of that would sort of mitigate that? The bias that would be introduced by just zeroing that out when MR is equal to 1. So one of the things we're saying is that by just zeroing it out when it's missing, we're saying that if you think about this itself as a variable, the missingness, right? We're saying that missingness, this variable r takes on the same value, or the same distribution with respect to the other variables, whether it's missing or not, right? Because these are both like, right, we're saying we have say we're just predicting something, y, is like x plus r plus mr, right? That's a very particular model.
Some kind of penalty for having a lot of missing?
Yeah, something like that. So yeah.
That's all I got.
Okay. So what I'm trying to get is interaction, right? So we can fix this to some extent by adding an interaction term. Right? We allow R and MR to be related. So we add an interaction term, lambda R, I guess put that R top, R MR. And that says the way, the slope of r, or maybe there's another variable in here, y, the effect r has on y, or the slope of r, whatever, can change depending on whether missing is on or off. So, so we can sort of stay in the regime of categorical analysis with these sort of indicator variables, and we may have to include, we can do tests and sort of say, does it make a difference if I include these interaction terms? So that makes it kind of similar to the complete case analysis in terms of the answers that you get. Yeah.
The reason why we add the interaction term because what?
Well, because implicitly what we're saying here is that there's only main effect for missing this on y. But because missingness affects the value of r, when missing is on, r is 0. When missing is off, r is not. We should include, at a minimum, an interaction term for r, mr, because they're definitely related. They're like very strongly related. And we might also include an interaction term for whatever other things we want to consider.
But what if we introduce interaction term, but whether we make assumptions that the interaction term is also a main effect?
Well, main effect just means that it's these things that depend only on the relationship only between y and mr. So if I'm including interaction terms, it's called an interaction term. It's like a main effect. It's contributing to the, but it's just allowing the influence of r to change depending on whether or not it's missing. You think about it that way, right? So it's imputing a value for r when it's missing, and it's allowing its influence to be different when it's not missing. So it sort of solves that problem of pulling our estimate towards whatever our imputed value is. It doesn't destroy the dependent structure as much. So I find these appealing, the additional value and the indicator variable approach in the context of this class, because rather than having missingness be modeled separately, they just bring missingness sort of into the model. Right? They bring missingness into the context of a categorical model. And so we can use logic that's closer to the usual logic we would use in the class. Okay, so another strategy. And this is going to lead to some other interesting things, is to do some kind of prediction and or randomness. Right, so on the side of randomness, and this is one of those things that's pretty easy to do, and it's good to do for a sensitivity analysis. You have a whole bunch of cases. These cases have an empirical distribution. So for example, you have 1,000 data points. 750 data points have a value, have an answer for question 3. The other 250 don't have an answer for question 3. Just pick one of the 750 answers for now. So graphical models, which are a special kind of hierarchical models, or log linear models. And in a graphical model, so we've been talking about the case where you have a graphical model like x, y, z are 3 variables, and this is the graph. And we observe a bunch of observations. Observation 1, x1 is some value, y1, z1 some value. Observation 2, x1, y1, y2, z2, and so on, right? But there's you can imagine a graphical model in which you assume that this structure holds, but there's one variable that you never get to see, a latent variable, latent or hidden variable. Right? Some factor that's invisible to you that's predicting the other thing. So that's your assumed structure. So the data actually comes to you as just x1, y1, or x1, z1, and we don't know what y is, x2, z2, and we don't know what y is. But we're still assuming a structure about it, that if we knew what y is, there was this conditional independence relationship. The way you describe this dependence structure is more complicated and isn't as nice as conditional independence, but there's ways to describe it, models that fall into that. So then we have parameters that we'd like to fit. It seems impossible to fit them. So what we'd like to do is to fit the parameters, assume that this is true, and fit the parameters of the original graphical model, the fully observed graphical model. So the parameters we want is like lambda ij, xy, and lambda jk, yz, or multiplicatively the exponential of that, and we want a theta for state xy and a theta for state y and state little z, right? For all states x in x, y, and z. So these are the parameters for what you might call the fully observed model. And those are the parameters we'd like to fit in order to fit that. So that seems impossible. If we had the full data set, so if we had the value for x, z, and y for each of the observations. So if we had all the observations y, we could estimate the parameters using maximum likelihood estimation, using Newton-Raphson or IPF or any, whatever technique, just plug it into the software. Right? We know how to estimate parameters for graphical models. Similarly, if we knew the parameters, we could do what we were doing with imputing missing data. We could figure out what the most likely values of the yi's were. Right? If I knew the parameters and I know x and z, I can decide what the most likely state of y is and fill it in. Right? And the problem, of course, is that we don't have either of those things. Right? We don't know the parameters and we don't know the value. But if we knew either, we could get the other. So the idea of the EM algorithm is to pretend we know the answer. In fact, because we're talking about log linear models, we don't, we don't actually need the y for every observation, right? What do we need to fit this model, to fit the parameters of this model? The lambda xy and the lambda yz. What function of the data do we need?
Because x and y, x is independent with the given the y, so can we just say we need a data set x and just independent with z? I think that's enough.
That's getting there, yeah. So what do we need to know? What's the minimum data that I need to know to fit these parameters? Right, so let me ask you a simpler question. Suppose I just want to fit an independence model on x and y. Do I need all the observations, x and y? Or is some summary of that table enough? What?
Yeah, I guess the summary.
A summary. What's the summary? What summary information do I want? What would be sufficient to fit it? Okay. So we just need the sufficient statistics, right? we need the counts. We need the counts. How many times did x appear? How many times did y appear? How many times did z appear? Each value, you know. How many times was x and I? How many times was y a j? How many times was z a k? How many times were xy equal to ij? How many times was yz equal to? So we just need the contingency table would be enough, right? I don't need all the observations. So the contingency table, you know, the vector. I have an x, which is which table. I have a y and I have a z. Right? If I just knew what all those counts were, that would be enough to fit the model. And I don't even need that. All I really need is, as we said, the counts that correspond to these two dependence relationships that I'm positing. Right? Okay, so I don't need to do the thing where I impute all the missing data, because right now we're saying everything is missing for y. I just need to fill in some cells. So I just need to fill in some cell counts. Okay, so the idea of the EM algorithm is that we don't know either of these things. We don't know the cell counts. We only have sort of marginals of the cell counts that come from summing over y. So we don't know the cell counts and we don't know the parameters. But if we knew either, we could get the other. So what we do is just pick something. So pick a theta called theta 0. Any theta. Right? Maybe it's I use normal random numbers, or I pick all ones or something. Okay? Don't pick all zeros. That won't work. So we pick some betas or equivalently to lambdas, just at random. And then we have two steps. One is called the E step for expectation. What do we expect the data to be in the cell? So now we have the parameters. I have some of the cell entries. So I have cell totals. Right? I have parameters. I have counts, partial tables, marginal tables. What do we expect missing ones to be? Right, so that's enough information. Knowing the parameters, knowing the probability distribution that's assumed, and knowing partial data, I can fill in the rest. So I fill in the cells. So note, there's no reason to expect that the entries that I fill in the cells will be integers. So this isn't going to be a very realistic imputation. But it actually works better to just use whatever the expectation is. So we know whatever the expectation under the parameter vector that I'm assuming of some cell in the table, I don't know, cell 325 is, right? Just fill it in. So I fill it in. I have now a complete table with all the counts. And from that, I can do the M step, the maximization step. Given these values, call them imputed values, maximize the likelihood to solve for a new theta 1. So I start with theta 0. I fill in the cells using the expectation. Then by predicting them essentially, predicting what the cells should be based on the model, then I use this step to go the other way and produce a new theta. So basically I'm going EM, just iterating. So it goes theta t, I keep updating my theta, etc. And the hope is that eventually this will converge. And then what we'll have is some sort of a sensible answer for this impossible question of what were these parameters. And what I can tell you is that if you think about the value, you think about the likelihood function that depends on the observed values. So there's a likelihood function, right? This thing is a probability distribution. I can plug into the likelihood function a parameter, and what I can say is that this weakly increases each iteration. So if I do this procedure, every time I produce a new estimate of my theta, the likelihood goes up. So the fit of this model, even with the hidden thing, this is going to induce a probability distribution on the observed variables, x and z. And I can construct a likelihood function, which is the probability that this happens times the observation. It's going to weakly increase at each thing. And when it's equal, when it converges, when the likelihood theta t plus 1 equals the likelihood at beta t, so when it stops going up, we're at a critical point. Of the likelihood function. Okay. Great. So does that tell me I got the maximum likelihood estimate?
Seems kind of hand-wavy.
Yeah, no way, right? The answer is no way. Yeah? I mean, if we're really lucky and there was only one, okay, then we're fine. Or if we were really lucky and we picked a starting point that was in the basin of attraction of the true maximum likelihood estimate, then we're fine. But in general, our likelihood function has got lots of peaks, especially when we start marginalizing things like this. We have a model like that where some of the variables are hidden, and all it guarantees us is that whatever hill you started on, it gets to the top. So in practice, a lot of people just run it once and call it a day. Don't do that. A better thing to do is if you're going to do this kind of algorithm, you run it, you start it, multiple restarts. You start either in a grid of points all over your parameter space or many random places, and you try to see that you get the same answer each time. And a more rigorous thing to do is that if you're really, if you're feeling especially algebraic, you can actually do an analysis that says how many peaks does the likelihood function have, and then you can show that you've found all those peaks. It's like with a univariate polynomial, you can measure its degree. In this case, this is like a degree of something more complicated, and if you find all of the peaks, some of which will be complex valued, you can prove that you found the maximum likelihood estimate. But usually the way to do it is just to do lots of random restarts. And if you're lucky, this is one of those things like, in theory, it's okay. So in these sort of models that aren't MCAR and MAR, what we have is that the observation is, whether an observation is missing depends on information that has not been recorded. So not missing at random, missing completely at random. M, whether an observation is missing, depends on data that was not recorded, right? And that dependence doesn't become conditional independence, doesn't go away when I include more data. So for example, it's good to think about examples when you're trying to conceptualize these things. So for example, maybe taking this class is predictive of both increased earnings and not answering questions about your earnings, because you understand how much you can get out of a data set. But then, or you take a survey, like the survey that is going on right now in this class for someone's project, and the survey doesn't ask if you took this class. Right? So it was an important predictor, it wasn't in the survey, and it affects both what one of the true values was and whether or not you report that value. And that would be an example of something where this violation is, the missing at random or missing completely random violation is violated. Another example would be, say you have a treatment, in a medical study you have a treatment, and the treatment for some of the patients causes a lot of discomfort or causes some symptoms that are really uncomfortable, and it causes them to drop out of the study, but you didn't measure that symptom, right? You didn't ask if it caused if they have headaches, or it didn't cause it if they had dry mouth or whatever, right? So you didn't ask if they had some kind of symptom, and so then this violation, this assumption is violated. So what are your options when you have that situation? Basically, you either produce some kind of model of the missingness, or you just ignore it and deal with the bias in your data. So most part so far, when we've encountered missing data, we've just ignored it and accepted the bias. But you should be nervous about that because that's not great. So what's another type of? I'm just going to talk about a couple of other types of dependence between missing dependence between missing data and outcomes. There's something called censoring. This is also a very common issue. So censoring is like you have some variable, often it's a continuous variable, and as that variable, maybe you have some categories here, and as this variable increases, at some point, you stop getting data. So every observation above a certain level is gone, or is either collapsed down to this category or just completely removed. So for example, I don't know if we go back to our example of drunken airlines. Maybe this is like severity of the crash. And at some point, when the crash is severe enough, there's like no data about anything because there's no black box or anything. Or you have some illness, or you have something like in the earning example, maybe people that earn more than 100,000 a year stop reporting their income, or only report it to be greater than that, right? And a slightly weaker version of that is something called you could call it probabilistic censoring. That's I. And that's just saying, this is, censoring is saying absolutely, when it passes a certain level of severity, no one reports it, it becomes missing. This is more like when it passes a certain level of severity, it becomes less likely that it gets reported. Right? Okay. You have a survey question that says, how much do you hate filling out surveys? Rate it 1 to 100, and everyone who rates more than 70, of course, doesn't answer the question. Okay, so that's censoring. So this failure to be missing at random or missing completely at random is kind of saying, right, so especially the missing at random is saying it depends on some piece of data that we haven't recorded in our study. So how do you get around that? Well, one approach, to approaching this missing at random is just to say, well, let's just keep throwing in more variables until we find something that is predictive, right? And then we find something that missingness can now be predicted from the data. We've soaked up all the dependence between missingness and the data. So for in the income example, maybe if we throw in enough variables, what's your occupation, what's your level of seniority, all those things, we can get enough data that we know more or less we can accurately estimate income, or we can accurately estimate missingness from the other factors, and it no longer has a dependence on income. You can think of it as conditionally independent. So we add more factors until m is predictable, or more precisely not predictable, but all the dependence between m and whatever it was that's missing has been absorbed by these factors that are now in our model. Of course, these are great, but of course, because the data is missing, it's going to be impossible to actually prove beyond a shadow of doubt that we've chosen the right model. To prove that we're in one of these situations. And so what do we do? Well, one of the techniques to think about sensitivity analysis, but another thing that makes sense to do is to, look at other studies Right, so we can look at lots of other studies that do include the variables to try to validate our assumptions that these variables are unrelated. Right? So you could say, here's the study I did, and I'm assuming that it's missing at random, and evidence that that's true comes from this other completely unrelated study in which I've picked up this relationship. Another thing you can do is to do a small validated sample. So in other words, you have a study of 1,000 people, and it's impractical, or 10,000 people. It's impractical to fill in the missing data for all of those, but you could take some small group, like 20 people, and track them down and figure out exactly what the missing data was, fill that in, and then use that as your sort of side study to prove that missing at random or missing completely at random was a reasonable assumption. Okay, so let's talk about some other approaches for dealing with the missing data when practically, like things people do and what that might cause. So one is what's sometimes called complete case analysis, which is more or less what we've been doing so far. That is, we just discard any rows or any observations with missing data. We just throw them away, and we hope for the best. Of course, if there's any sort of dependence going on, if there's censorship, if there's any of these other possible dependence between missingness and the data, this is going to cause some kind of bias. In estimates, larger variance, right, because we've thrown out data points, weaker power, right, harder to get significance, because we've thrown away data. Right, so it's always sort of makes you nervous, or should make you nervous, to throwing away data. So you can have a systematic bias, and you might not have, especially in some example with a massive survey where almost every question has at least, almost every observation has at least one question that people didn't answer, you might be left with almost nothing, right? Or a very, very biased subset of people that answered every question, right? And, so a little bit more subtle way to do it, which I think points toward something that's more principled, is an available case analysis. And by that we mean, well, you're often not interested in every possible question of the data, right? We're only interested in kind of doing a complete case analysis on sub-questions, right? So we have specific questions we want to ask of the data. We take giving that question, maybe a lot of the missing rows don't matter, right? So when we cut out a bunch of the questions in the survey, for example, we have a larger complete case to answer some subset of the questions, or we've grouped them, or we've merged them somehow. So in this situation, each model that we contemplate might use a different sufficiency statistic, right? And it's kind of marginalizing over other questions, over some variables. So a lot of the missing data shows up in variables that we're marginalizing over. So in some sense, we're not reading it, so it doesn't matter that we don't know what the value is. And each model keeps the rows or the observations that are complete for its question, and uses different data. So if we're doing something like analyzing different models to see which one fits best, and we're doing an available case analysis, it's a bit strange because we're actually using different data sets for each model. And that's sort of, okay, if they're wildly different, then that's sort of awkward. Okay. But as I mentioned in the beginning, often one of the more appealing ideas is this imputation strategy. More appealing is to impute the missing data points, to fill them in somehow. So let's talk a little bit about imputation strategies. Strategies for filling in the missing data that don't, well, where we're comfortable with the trade-off that it causes. None of them is going to be perfect. So the idea is to fill in a plausible value. Or more accurately, what we'd like to do is fill in values that don't mess up any of the inferential questions that we're interested in, which might not be the same as a plausible value. There might even be impossible values, we'll see, which are quite good choices to fill in. So plausible in what way? And what do we mean by that? And we want to understand what the bias of the result is. Right? What bias have we introduced? For example, so we have a lot of uncertainty about the missing value. If we plug in a single value for it, we act as though we know it. And so at a minimum, this is going to change our, most likely change our standard deviation or our measures of variance for the imputed variable. So in the extreme, we'll say a few words about missing data. So missing data, so most of our methods kind of implicitly assume there's sort of a couple of ways that the data can be missing, right? So if we think about the data as coming in rows, where I have variables like x, y, z, and this is observation 1, observation 2, I might have, this is some number, or this is some category, y some category, z some category, and maybe here I have a missing point. Oops, these are all ones. And I keep going, right? So I can have some spots that might be missing in my observations. And you can also think about maybe in a table, entire, like a contingency table, I could have entire cells that were missing, which is sort of something different from a structural zero, right? It's a whole cell that's not there. And most of the time, this is the situation, right? You've got a survey, for example, you ask lots of people a bunch of questions, and people choose not to answer some of the questions. Right? That's a typical thing. Or there was some problem with the data collection process, and it caused a problem. So there's a lot of different sort of models of missing data, or ways to think about what happened, the process that generated the omissions. So for example, there's this thing called monotone missingness, which is sort of a bad thing. This is like when an individual drops out. And we're not saying even why they did, but for example, we could be doing some kind of a longitudinal clinical study or something, and we have an observation every year, and then at some point someone drops out of the study and never reports again. And so this is like the pattern where once their missing data has begun, it continues for the rest of the study. There's missing completely at random, which is kind of a good situation, or the best situation. And what this says is that the probability of being missing, so the probability of a cell or a row being missing, has nothing to do with the rest of the observations. Of an observation being missing is independent. So in other words, you could think about your study if you had, like in this example, we had 3 variables, x, y, and z that we're interested in. You could think about there being another variable, m, which stands for, have I deleted this entire observation? Is it missing? And then the rest of these would be hidden. And what we're saying in missing completely at random is that m is independent of x, y, and z as a random variable. Right? Another way of saying that is that this marginal, the marginal corresponding to missing or not, is the same, right? The probability of being missing is the same regardless of the state of the other 3 variables. Right? So that's like the best possible situation, and when we're in that situation, there's very little that we have to do. You know, we can throw out the rows, we can do various things, and it won't mess up our conclusions. Of course, it's impossible to prove that that's the case, and rarely is that actually the truth. But that would be the ideal situation. There's something which sounds the same but is weaker, missing at random. Missing at random means that the conditional distributions are the same. In other words, the distribution of the missing given the rest of the variables and missing given the observed part of the rest are the same. That's a little confusing. So let me say this in a couple of different ways. So another way of saying that is that the missingness depends only on observed things. So there's no kind of hidden relationship between the variables that we don't observe and whether or not we're actually missing. So for example, suppose I do a survey, right? So I do a survey, and in the survey, I think about the design as having 2 parts. I have a demographic, like I decide who I'm going to ask the questions of. You know, I choose people of certain genders and races and ages and income levels, whatever, right, from some database. And then I call them up and I start asking them questions, or I send them an email, I start asking them questions. So there's a demographic and there's a survey. And so a missing at random is something like, you know, suppose there's a survey question like, you know, what is your income, right? And some people feel uncomfortable about reporting their income, so they don't want to tell you. But suppose that I can completely predict, or all of the predictive power for who's not going to report it comes from the demographic and not from other questions on the survey, right? Or from that question itself, right? So in other words, whether or not income is reported it doesn't depend on income, given that I know the demographic or given that I know the other questions. So that it's a little bit subtle, but it's the idea that, you know, whether the data is missing depends on things we observe. Oh, I guess that's the same thing I said there. Things observed. Okay. And not what and it does not depend on what their answer would have been had they answered the question. So it's not doesn't depend on what's been suppressed. Okay, so these 2 cases, missing completely at random and missing at random, these are our sort of best possible cases for missing data. So these are the situations in which we don't have to do a lot of heroics to get our analysis to work. So in other words, analysis using observed data is not systematically biased. And we may still decide that we want to impute our missing data using one of a variety of methods that we'll talk about later. So, from the point of view of a user of software or user of the techniques that we talked about in this class, of course, it's awkward to deal with missing data, and the nicest thing is if we can just fill something in for all of those entries that we didn't have. Of course, you can introduce a lot of bias when you fill it in, and this filling in process is called imputing. And so we'd like to know both when is it okay to impute data, and what are the methods for imputing data, and what are the things to watch out for when we do that. So a lot of techniques will just do that. They'll essentially fill in missing data according to some rubric or some method, and then you just go ahead and apply your techniques that you would normally apply as if the data set was complete.
Yeah, excuse me. I was wondering, besides the systematic bias, I was wondering, do we have any other kind of bias kind of involved into our data besides the systematic bias?
Well, what we're saying is that this is the situation in which it's more or less okay. So using sort of a likelihood method won't create a biased answer. It might, not give you power, things like that. But as I continue to talk about other ways that it can be missing, we'll see other types of errors that can get introduced. Yeah. Okay, so the kind of methods of imputing the data that we can do are, simple things like just plug in the most likely thing, or plug in the average thing, or the mode, or the mean if it's a continuous thing. We can try to build a model essentially of that variable as the response and make predictions. We might plug in the most likely prediction, or we might do some kind of sampling scheme where we randomize that prediction, because if we just plug in the prediction, then we get kind of a reduction in variance that's not accurate. And then we take this new fixed data set that we've generated somehow and use our usual methods on that. And as always, with this kind of mucking about, if you're doing this, it's really good to do some kind of a sensitivity analysis. So there are more than one technique that you can use. There's more than one assumption about missing data. You should try a couple of different strategies and hope that they don't give wildly different answers. If they do, then that's a cause for concern. If they give sort of similar answers, then it's an indication that you understood what's going on. So some of the alternatives include things like what's called a selection model. So an alternative, in other words, an alternative to missing completely at random and missing at random, is some other assumption about the distribution. So a selection model is something like we have a density function on the outcomes model without the missing data. We have another function, another probability distribution on missingness given the outcome we observe. So we have a model of missingness. There's sort of two things that can happen, and then we can think about there being some kind of an arbitrary joint distribution which deals with both the missingness variable and the outcome variable. And a selection model is one that assumes that this distribution, the joint distribution on whether or not the data is missing and what the data is, has the form a model that without the possibility of missingness times this probability of missingness. And so that's not quite the same as the other examples. I guess it's close to MCAR. And then there's also this sort of pattern mixture model which says instead we factor, let's give it different parameters, like this, times f of mx, where y's distribution, we have some response variable that we're interested in, and it is conditioned on missingness. Uniformly at random, to fill in missing, to compute. In other words, so for each of these 250 that don't have an answer, just select, pick is a very easy function to write. Just pick a random value of one of the other 750, so it will have the same distribution as the other 750, right? And plug it in. So what's the advantage of that? Well, it doesn't change estimates like our estimates of the variability of the 750 of that question, of question 3, right? Because we're drawing it from the same distribution, so it won't change much the estimates of variability. And so our kind of all the standard deviations that involve this question won't be as messed up. Of course, the disadvantage is that it assumes that this variable for those 250 has nothing to do with the rest of the variables. So you would think, okay, what's better? Well, we should try to draw not from the uniform distribution on the rest of it, but on some predicted distribution. So the other extreme is to say, okay, we're going to draw from a predicted distribution. The predicted distribution we're going to draw from is just a point, just a single possible outcome. So at the other extreme, what we could do is to fit a model on the non-missing entries. So we'll do sort of a complete case or applicable case analysis and observations. So here on the 750. So we think of that as our training set. And then just use that training set to predict the value for the others, right? Fill in predicted value for the rest. Okay, so we have a perfectly good model. We can learn on the cases that we have enough information. We fit that model, and then we just fill in the most likely value for the rest of them. Okay. So this can work very well, but you also have to watch carefully. Of course, it can produce spurious results. It also suppresses the, okay, so it can be spurious. Careful. It also suppresses variance. Right, it's kind of opposite of this one where there's lots of randomness. Here, there's no randomness left, right? We're just filling in the expected value for each of these things, and we're not allowing for the noise that that in the real data set would appear, right? So in the real data set, there's no way that, for every one of those 250, it was exactly the predicted one. So that's going to overstate the dependence between that variable and the other variables in the set.
Dr. Morgan,
Yeah.
for that, like how we do cross-validation, we kind of look at the predictive power.
Mm-hmm.
Can we just do that to decide?
Yeah, it would be reasonable to do a cross-validation.
Smaller chunks.
Yeah, that would make a lot of sense for that. Yeah, for that context, absolutely. But even better, that will tell you what these, right? It'll help you check if it's creating some spurious relationship. In other words, he's saying, just look at the 750, pretend that you don't know, zero out, randomly pick a subset, make them missing, and then do the same analysis here and see how good it is. See if it's close to what you get. That's a great test, right? So I may even write, should do cross-validation if you're going to do that. Right.
Yeah, I used to.
Yeah.
Related to this question, I was wondering, so usually we do a 10-folded cross validation or just do the 2-folded cross validation?
No opinion. I mean, there's a literature about that stuff. I'm not going to touch on that. Read the literature about which how to choose your cross validation.
Cross validation. But it does not matter to us.
I mean, it depends on the size of your data set, and variation, and things like that. So, yeah, no idea. Okay, so what do you do? So suppose you do this, and your cross validation says, "Wow, the variance has been suppressed brutally, and there seems to be too strong a relationship between this and everything else, and I'd like something that looks more realistic. Right? I'd like imputed data that's more realistic, that more realistically represents the natural variation that I would see, the noise that I would see, that doesn't say I have a perfect prediction. Maybe if your procedure is really good, you can adjust your results that way. The other thing you can do is you can combine these things, the idea of random and predicted. Imputation. So in other words, what we're doing is we're saying our task is not to predict a value, but to predict a distribution. So we train on the 750. Maybe we have a multinomial model that we get out. So train on the set where we have complete data, get a multinomial model, if it's a multinomial response. The missing data, now I have outcomes red, green, and blue. For observation, 210, it thinks, based on this model that I trained, it thinks the probability of red is 1/2, the probability of green is 1/4, and the probability of blue is 1/4. Right? So the pure predicted one would just say fill in red for that. Right? This one would not use this distribution, but use that's based on observation 210, but use the one that's unconditional, right? The one that just marginalizes out everything else. Right? And so this would say, okay, do that, and now choose one of these values at random, according to this distribution. Okay, so that's kind of combining the best of both worlds, if you're lucky, in that the predictions that it's going to make reflect what you've learned about the data set from the full examples, but its variation is more realistic. Sort of accurate. So this produces a data set that someone else might not be able to tell you imputed it, right? So most of the other examples we've given, if you analyze the data, you'd probably be able to notice that it had been filled in. If you do it this way, a casual observer will not be able to detect that you imputed the missing values, because it's not statistic. You sort of use all of the statistical information that you had in order to make that prediction, so you won't see anything funny happening. So it's a more realistic data set. Of course, you'll get a higher error on the missing values than from that one, because you've thrown away some information by adding the noise. And so one of the other things people sometimes do to sort of make more of a compromise or a slider between totally random and totally predicted is to do what they call multiple imputation. And so that says, instead of doing this once, you do this several times. You do it 5 times or 10 times. and then you average the results. So you do it, complete your statistics, you'll get a little bit different answers for all of the questions that, for the parameter values, and then combine that information, average the parameter values together. Do this multiple times, average results. And a related class of algorithms for dealing with missing data are Monte Carlo algorithms. That's sort of where we're going with this sort of approach, where we sort of drift around, we do lots of draws, and see how that changes our parameters. I won't get into the details of how that works, but that's sort of this is sort of the first step of a Monte Carlo. Yeah.
But the result is imputed into the missing data, about the average result.
Oh, well, I mean, depending on different things you might do. I would think that what you'd probably do is to a simple way to do this, which is perfectly reasonable, is use this technique. Okay, let me put it this way. You take this, you do this, right? It's gonna, and you're interested in some question, like, what is lambda x, y, ij? What is some interaction parameter? Does smoking cause cancer, or whatever, right? You're interested in some parameter. Each time you do this, you're gonna get a slightly different answer to this parameter, right? It's a little bit like the stuff I showed in the R sheet in the beginning, where I did at the end. I was trying to estimate p. I was trying to estimate the bias of a coin, and I ran the same experiment with some number of draws many, many times, and I found that the estimates looked like that, right? And the true value was like here. So the idea of this is that you do that. Run this lots of times. You can make a histogram, or you can just take the average and pick the thing that ends up in the middle. Yeah, that's the idea. So you're sort of repeatedly running this experiment, repeatedly imputing the data and seeing if, on average, what kind of answer you get.
Well, yes, I related to this question. So if we want to use Monte Carlo algorithm, but we're assuming that the shape of data is not a fat tail. But if the shape of the data distribution is a fat tail, that means we have like the extreme value gonna affect our result, right? If we want to take the average. Like for example.
Yeah, right. If this, I would be sort of surprised if that happened in this case, because we're doing a multinomial. So because of the structure, the structure we've chosen here, this should be asymptotic. This should be normal, because of this multinomial, essentially. If it's not, that probably means that there's a singularity. So somewhere in the model, for some choices of this, we're hitting, just like in this one, when did this one depart from normal? It departed when there was a problem with the confidence interval, right? When you flipped the coin 10 times and you got heads every time, that messed everything up. So if this departs from normal, what I would expect is that you're hitting a boundary. Yeah, and then maybe you want to change your strategy. Yeah, that's a good question. Okay. So in the last few minutes, the last topic I want to talk about is kind of, it's not directly about missing values, but it's an idea that is another sort of more careful way of imputing them. And it's called, it's also popular, and it goes under the heading of the expectation maximization algorithm, or it's often called the EM algorithm. And before I talk about what it does with missing data, let me tell you what it does in the case of a very simple kind of missing data. And I'm going to restrict to the case of graphical models. It seems very hand-wavy and like a disaster. In practice, surprisingly often, it really does find the global maximum. Because in practice, kind of data is sort of nicely generic enough that it seems to work. Although it's not hard to construct an example where it would fail.
And they just use the EM algorithm for doing, I've heard of this before, just for doing like missing data stuff.
So I'll talk about it next. So this was an extreme case of missing data where every single observation here was, but you can imagine there should be some way to twist this a little bit to deal with only some observations being missing. And next time I'll say a couple words about that. So that's sort of a more, in some ways, more principled, really modeling the data, filling it in, and doing this kind of a likelihood approach. All right, thank you.